Okay, so let's find together some work, the work of the weight and the energy, the kinetic energy, and then the angular velocity for a slender rod. So we have a slender rod, up, and that's the position, the initial position at T1. Okay, and let's say we want to find the final velocity, angular velocity at T2 when theta, so that's my reference for theta, when theta is equal to 90 degrees. Okay, so first we need to find the work of the weight and that the only force. So if we draw the force, let me draw all the forces. We have the weight applied at the gravity center at the position 1 and position 2, and the force that we don't know, we have the reaction at the pin. But those two forces don't work because there's no displacement. Oh no. I click on this. Okay, let me put my pin again. Boop, 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 and boop. So again, those two reactions don't work. So we don't include them in the principle of work and energy formula. So let's find the U for the weights between T1 and T2. So this position, we need some dimension. We need the length. So this one is the length of the rod. So it means that the weight, the delta Y, is L divided by 2 at G. Okay? The gravity center goes from this position to these positions, and the difference on the Y is L divided by 2. So it's the weight M times G times L divided by 2. And it's plus because the slender rod is going down. Okay? T1 is if it's released from rest. T1 is equal to 0 because it's released from rest. And we can increase the difficulty later, but it is, let's say, simple case, T1 equals 0. T2, how much is T2? It's rotating about, let's call this point A. So for rotation about a fixed axis, the kinetic energy is 1/2 of IA omega square. IA, it's a slender rod, about A, it's 1/3 of ml square. So it means that T2 is equal to 1/2 of 1/3 of ml square omega square. So T2 is equal to 1 divided by 6 ml square omega 2. So now if we apply the principle of work and energy, we have T1 plus sum of the work between 1 and 2 is equal to T2. T1 is 0, it's released from rest. The work for the weight, we find mgl divided by 2. And T2, we find 1 divided by 6 ml square omega square. And the goal is to find omega. Okay, so we can simplify it. We have m on both sides. We have L and L square, so this one loss is square, and 2, that becomes 3. So we have 3, I put it on the other side, so 3G, and the L divided by L is equal to omega square. So the omega is equal to the square root of 3G divided by L. It's a L. So the velocity, the angular velocity of the rod at 90 degrees is omega, is omega, and at the square root of 3G divided by L. And the work of your slender rod between the position 1 and position 2, between 0 degrees and 90 degrees, is mgl divided by 2. Now, if you want the position of a slender rod, let me just make a small break. Okay, so if you want to do the same thing for T1, but let's say we are at any position, oops, any position theta. Okay, and it has been released from rest at T1. Okay, there. T1 equals 0 for theta equals 0. Okay, so now the distance between W and this one is this distance. Let's say I call it H, and we have L divided by 2. Can you see that? Oops. This one is L divided by 2 there. So this distance is L divided by 2, this one, and this angle theta. And we want to find, I'm sorry, we cannot, let me clean this a little bit. Okay, slender road, G, this distance is L divided by 2, and we want to find this delta Y there, okay? And we know that this is angle theta. So that sine of theta, that is equal to delta Y divided by L divided by 2. So delta Y is equal to 2 sine theta. L sine theta divided by 2. Okay, that means that the U, the U for the weight, the work of the weight, it's equal to L sine, let me write mg first, so the mass times g times the delta y, that is L sine theta, divided by 2. Okay, and that's for any theta if we begin from this initial position. And T2, it's equal to the same thing. There's no theta involved there. So it's equal to 1/2 of IA omega square. So T2 is equal to, I found it there before, 1 divided by 6 ml square omega square. Okay, so now if we sum, if we do the principle of work and energy, the T1 that is equal to 0, let me write this, I'll make a bit more space. So if we write the T1 plus sum of the work from 1 to 2 is equal to T2. We have 0 because we say it's released from rest. If it's not released from rest, we need to add omega, a kinetic energy using omega 1. This one is mgl sine theta divided by 2. And this one is 1 divided by 6 ml square omega square. So we can simplify. Oops, can I move this a little bit? Yes, thank you. So no m, L and the square, and the 2 begins, and the 6 begin with 3. So we have G sine theta, and the 3 on the top, and the L on the bottom. And for W square, so we need to take the square root of all of this. So that's the angular velocity at any position for a slender rod that is released from rest on the horizontal position. So let's write it. Omega is equal to the square root of 3g sine theta divided by L. Okay? And we can find that for 90 degrees, so for 90 degrees, the sine is equal to 1. So we come back on this formula that we just proved before. Okay? And it works for any sine theta. So that's it, and that will help you to answer your question for your quiz. Bye bye.